Yeah, so I'm going to talk about the project 6G Goals, which means 6G goal-oriented AI-enabled learning and semantic communication networks. So in some way, so I'm a member of the management team, and in some way, this project complements the previous one because we have the same coordinator, but a different set of partners. So coordinator is Sea Leti, with Emilio being at the helm of the project. And then the technical manager is Knit from Italy, Paolo Di Lorenzo. Innovation manager is Vincenzo Ciancalebore from NEC. And then there is from UK is Toshiba and Imperial College. And then we have the HPE, Hewlett Packard Enterprise, both from Italy and France. We have Eurecom from France, Telecom Italia from Italy, and Aalborg University also as a partner. But we also have affiliated partner from Asia, which is basically the Singapore University of Technology and Design, which have a large experience in Open RAN and integration of AI modules in the systems. The semantic communication was mentioned before, and you can say that then the way this project complements the previous one is that it builds the higher layer for integrating machine learning modules and integrating basically understanding of the data that is being transmitted in order to make the overall communication more efficient. So, the assumption that is often taken is that because of the universality of the communication architecture, usually the data is transmitted without prior understanding or how informative the data is, which is a semantic, or how useful it is for a certain communication goal, which is usually in real time. So the technical problem of communication is how accurately the symbols are reproduced at the receiver side, how accurately they are transmitted. And then this is how we are building the protocols that are moving bits back and forth and trying to accurately retrieve the bits, because the assumption is that each bit is useful. Of course, after doing the source coding. But the point is that the context in this network is changed, and the key change compared to the previous generation is the introduction of AI and machine learning modules. So the side knowledge of every node in the network is constantly changing. So we need to basically figure out what is useful and what is meaningful information to the destination, and based on that, just adjust the communication method, the coding, and the amount of data that is being sent. So at the marketing level, you can say, how could we say less but understand more? And that is the interplay between the machine learning that is integrated in the network and the transmission of data. So if we see what is targeted by this is the attainment of sustainability, scalability, and interoperability. So you can say that the edge AI ML modules and 5G, 6G systems have been, or let's say the cellular system have been designed and operated as separated silos. And the point is that if the AI modules are not designed in concert with the underlying wireless interface, then there could be waste in terms of transmitted data, because most of the data is not used. So maybe we can have excessive signaling or transmission of data that in the end doesn't end up to be useful within certain real-time operation and so on. So the point here is whether we can only send useful data that is sufficient to infer the context of communication, for example, the signaling information, and the data which needs to be used in a certain fulfillment of a goal or a task. And then this can reduce the overall file layer complexity by targeting lower spectrum, less antennas, and so on. But it's also interesting to say that from the physical layer, this semantic communication will use all information modalities. So it's not only communication, but will rely on the sensing information and also localization. The focus is on the transmission of relevant, valuable, and timely information, which is often called pragmatic communication in linguistics. So if we look into the three different levels of communication, at the bottom we have a technical communication. On top of it, we have a semantic communication, which is kind of interpreting the transmitted data within certain context and knowledge. That's why we have this knowledge sharing. And finally, we have the effectiveness or pragmatic communication that attains some goal within a given context. So for example, if you look into the new cars, or some of the electric cars like Tesla that have screens that represent the environment, you can say that the communication from the car to the person is semantic because they are representing the sensory data with a certain picture of, I don't know, bikers, pedestrians, and so on. That's a semantic representation. But what is effective information is which of these data can lead to, is actionable, basically can lead to action that can achieve certain goals in terms of effectiveness or safety. So the concept in the project is that we have, based on observation and possession of certain concepts, we have to make informed decision. And in principle, the hypothesis is that the communication can be made more efficient by relying on this prior knowledge and by understanding what the application, what the goal of certain application needs. And what we want to do is to lay the theoretical, algorithmic, and operational foundations of this novel communication and networking paradigm. Just to give you an example, if you take the classical communication theoretic model, then we are having a certain entropy, so uncertainty of the destination about the source, and this entropy is conveyed by the communication. But when we have machine learning model, maybe we can send initially a certain neural network model to a destination to teach the destination how to interpret the upcoming data and then make the communication more efficient. So one of the ideas in the project is exactly this, to decide when to transmit the learned model rather than individual data. So basically, this would mean that you may make the communication more efficient, not by only looking into antennas, network densification, classical spectral efficiency, but you look into the overall interplay between the AI modules and the communication modules. So the effectiveness is measured as a measure here is not a spectral efficiency, but certain effectiveness or accuracy per goal or per transmission outcome. So we are actually focusing on we will try to define measures that are measuring the actual effect of the received information rather than evaluating information only in terms of spectral efficiency. So the data paradox is that AI needs data, but data needs AI. And this is where we have this idea of deciding where to send raw data, where to compress the data, or whether to send a model how to interpret the data, which would be basically some form of initialization protocol for communication. And this is going to lead to understanding and effectively conveying the intended meaning. So once we establish a certain level of common context and knowledge, then we can communicate within this context. The problem is, how do you put this within a given network architecture? And this is why we are having a proposed architecture. So instead of just saying we're going to add AI modules here and we're going to design protocol there, we are trying to define this semantic radio access network controller, which is going to orchestrate both the data that is known by the nodes and what is being transmitted, as well as how these models are updated when the nodes are interacting with each other. So this is what we call AI native 6G system. And another thing that we are using is a form of causal modeling, causal inference. So instead of, so when we have interaction over a wireless channel, instead of just taking the data back and forth, we are going to, in a real time, build causal model about the controller or about the actuator, and then based on that, try to interpret what the incoming data means. And this can lead in a critical operation to defining what is a safe state, for example, which action is possible to take, which action is absolutely forbidden to take, and so on. So this is kind of interpreting the transmitted data within a certain causal model. And there are two proof of concept planned. One is for a point-to-point link, where we aim at TRL4 maturity, and we want to show that we can, by having trained neural networks at both sides that can interpret each other's communication, we can actually improve much more efficient communication over a limited rate wireless channel.
May I ask you to wrap up because you're running over time?
Yes. This is the last slide. So, and the last one is interaction between multiple robots that cooperate to achieve a certain goal. So that's it. I guess I'm not too much over time. So get in touch with us, also with our coordinators, project coordinator and technical manager. And we have put some more details into one of the early papers that is based on our proposal text.
Many thanks, Petar. You managed to wrap up spectacularly fast, so we're again on time. Thank you so much for that, and thank you so much for your very interesting presentation.